And because everything has that same amount of energy, wave theory says the frequency and wavelength are always going to have to stay the same. But Compton found that that was different because he hit those X-rays on various types of materials and found that the wavelengths that left the material were much longer than the wavelengths that initially hit the material. So he thought about it in terms of a collision. These light rays are made up of electrons. They're having to excite electrons. When this light hits the surface and those electrons absorb some of that light energy, some of the energy that's being brought with this light is being absorbed or transferred to the electrons that are in the material. They can't get that back. So then that means that some of the wavelengths of the light that leave that object, it can't have as much energy. And because it doesn't have as much energy, that means the wavelength's going to have to change, and that means that the frequency had to have changed. So if that energy decreased, that means that the frequency had to have decreased. And we know that frequency and wavelength have an inverse relationship. So if frequency decreases, that means that the wavelength must increase. So the wavelength must get longer, okay? Let's go through that one more time, because I know that's kind of a lot to think about. So let's do one more time. According to wave theory, frequency and wavelength typically stay the same. And they truly believed that. And they thought that Compton, again, like we said, was crazy because he found that when a wave hits a material, when the wave leaves the material, its wavelength is longer than what it was when it initially hit that object. Compton had to think about an explanation as to why this happened. And he thought about collisions. So he thought when that ray of light, or when that X-ray hit the object, the electrons that were in that object absorbed some of the energy from that X-ray. When they absorbed some of that energy, that means that the X-ray had to transfer a little bit of its own energy into those electrons. Because it transferred some of that energy, that means that the X-ray itself had to have lost a little bit of energy. Now, the total amount of energy is still conserved because some of that energy just went to the electron. However, if we're thinking about the X-ray itself, it lost a little bit of energy. So when it leaves the material, when the X-ray leaves the material, it doesn't have as much energy as it did before it hit the object. So because of that, if the energy decreased, it means the frequency also had to have decreased. Why is that true? Because Einstein said that energy and frequency are directly related to one another. So because of this, if the frequency decreases, the wavelength must get longer. So this was his explanation as to why he truly believed that what he was seeing was true. Okay? And again, a lot of people at the time didn't so much believe him, except for those modern physicists. But now we know, according to what we know today, everything seems to still have fallen in place. So we still believe him to be true today, because it's what we see. Okay guys, so we are on the last section that we're going to do in chapter 27, and that is about the Bohr model. Now, we've already talked a little bit about the Bohr model at the beginning of this, of these videos, and, okay, in the 1800s, there was lots of work that was being done with gas discharge tubes. So kind of what that means is just a lot of old dudes were trying to do different types of experiments, and especially with light, just with tubes of gas, so like glass tubes that just have gas particles in them. We know that light from an incandescent source, so that just means like a light bulb. So when I say incandescent, I just mean like a regular light bulb that you have in your house. We know that light exhibits a continuous spectrum. So what that means is I see all of the colors of the rainbow. I see Roy G. Biv, okay? This spectrum of light that comes from a tube, that comes from like a light bulb, we call that an emission spectrum. The reason that we call that an emission spectrum is because light is being emitted from a source. So an emission spectrum is just happening when light is being emitted from a source, okay? We don't just have emission spectrums, we also have absorption spectrums. And absorption spectrums is just when atoms in a substance absorb light energy. So we call that absorption spectrum. If you will look for me on slide number 22. So if you're going to look at slide number 22 for me. On slide 22, over to the right-hand side, I have 3 different pictures for you. There's a continuous spectrum, there's an emission spectrum, and there's an absorption spectrum. So the continuous spectrum is where we're seeing all of Roy G. Biv. The emission spectrum is what we see. Emission spectrum is what we see when light is being emitted from a source, and that absorption spectrum is what we see when light is being absorbed by a source. Okay, typically it happens within a certain way. So usually hot gas is really good at bringing out emission spectrums, whereas cold gas is really good at absorbing energy. So cold gas typically will give an absorption spectrum. I don't think that you're going to have a whole lot of questions on this, but I at least just want you to see what those look like, okay? So I get the emission spectrum when a light is being emitted, and I get the absorption spectrum when light is being absorbed, okay? Now, the dark bands in those two spectras, the dark bands are just where all of that light is being absorbed. And you see color when light is being emitted. Okay, so that's a way that you can read those. Let's go on to the next slide, which is slide number 23. And this is really where we're starting to talk about Bohr. So Bohr developed a method to find the quantized radius and energy. And we have some formulas here. Let me write those down for you guys. Okay. So to find the amount of energy for this atom, to find the amount of energy, Bohr came up with a formula . E equals a negative 13.6 over n squared. And this is in electron volts, so that's why I wrote this to the side, because his energy levels are in electron volts. So his energy is a negative 13.6 divided by n squared. What does the n represent? We've talked about this at the beginning. You should say that n is equal to your energy level, and that's something that they have to tell you. So your energy level, if you're on the first row of the periodic table, what's your energy level? 1. If you're on the second row of your periodic table, what's the energy level? 2. Third row of the periodic table, what's your energy level? 3. Fourth row of the periodic table, what's your energy level? 4. So whatever row on the periodic table we are, that's the energy level, okay? Let's see, I thought there was another one I wanted to give you. Oh, there is. Okay, to find the radius for an atom, let me write this one down for you. To find the radius, Bohr found that I'm going to take the square of my energy level and times it by 0.0529. And he said that this was in nanometers, so he already accounted for the type of unit that there was. So to find my radius, it's going to be 0.0529 times the square of my energy level. Okay, so Bohr believed that these calculations led Bohr to believe that electrons can radiate energy only when they move to a lower energy level, and then they're going to absorb energy when they move to a higher energy level. So remember that Planck and Einstein already said these types of things. Planck said that electrons can absorb a bunch of energy. Einstein then said if if electrons can absorb energy, then electrons can also emit energy. Well, Bohr's just saying the exact same thing. So Bohr's saying that electrons can emit energy when they're trying to move to a lower energy level, and they're going to absorb energy when they move to a higher energy level. Okay, so this next problem, this last slide on page 8 for me, but that's slide number 24, this would be an example of how we could find the radius and the amount of energy of an electron that has a principal quantum number n equals 3. Principal quantum number just means the energy level, okay? So I know that this electron is at the 3rd energy level. So let's solve for both of these things, okay? Does it matter which one you solve for first? It does not, because the only thing that these things are really dependent on is the energy level, and we know that. So let's find the radius first, because that's what they asked for first. So I know that my radius is equal to 0.0529 n squared. So my radius is equal to 0.0529 n squared. I know that my n is 3, because that's my energy level. So I know that I'm in the 3rd energy level. So I'm going to take 3 and square it, and then I'm going to multiply that by 0.0529. When you do that, you should get 0.476 nanometers, because remember, Bohr found that this was already in nanometers. So I have 0.476 nanometers, so that's my radius. Okay, we were asked to do the same thing for energy. And I know that energy is equal to a negative 13.6 over n squared. And that's in electron volts. So I have negative 13.6 over n squared, and that's in electron volts. So I know, again, n is just 3, because that's the energy level that we're at. So I'm going to take a negative 13.6 and divide it by 3 squared. So it's really like I'm taking negative 13.6 and dividing it by 9. And when we do that, we should get a negative 1.51 electron volts. So my E is equal to a negative 1.51 electron volts. Okay, so that one's pretty easy. That one's pretty straightforward. All right, let's keep going. We're almost done, guys. Almost done. Okay, so according to Bohr, Bohr created this model for the electron. And Bohr said that electrons must be on energy levels. I can't find electrons in between energy levels. So it's kind of like what we did with sodium at the beginning of this chapter.